I've handed you all back your exams. It was the same grading scale as the first exam, so the scores weren't real high, but the grading scale was fairly generous, so things sort of balanced out. Remember that, yes?
Notice the grading scale like posted yesterday.
Uh-huh.
It's different than that one.
It was different than that?
Yeah.
What did it say?
85 to 100.
Okay. I must have typed it in wrong because this is the one that I have in my grade book. So, so the only difference was 85. Okay.
So everything was shifted 5% up.
I will try and look at the email and send out a new email, but that is what I meant to write. Sorry about that. Okay. Remember that the final exam will consist of questions from the exams and practice exams verbatim, so you have the solutions to both of those. So that's part of the final exam. There will also be part over the last 3 chapters. So you may see these questions again, and it would be useful to go over them. You have a homework assignment due. It's Friday, but it's not this Friday. It's Friday after that, November 15th. So we got a little bit of time. We'll begin to start talking about some of those problems, but no rush on that. Okay, so what we're going to start now is Chapter 7, which is about really mainly about the extracellular fields produced by nerves and especially the heart. And we're going to end up talking about the electrocardiogram and some of these other issues. But today we're going to start off talking about something a little different, and that is electrical stimulation. And this is covered a little bit in the chapter, but it's also covered in some of the homework problems, not necessarily the ones on the assignment, but some of the homework problems at the end of the chapter. So I want to talk about electrical stimulation, and this is very important because we're talking mainly about neural stimulation today. And you can have all sorts of applications of neural stimulation as to restoring people's ability to hear, to move, all sorts of activities. So this discussion will have a lot of applications. We won't get into the applications in detail, but we'll understand some of the basic mechanisms underneath it. All right, so we'll begin with one of the problems from the book. Problem 7.38. And this problem rederives the cable equation with a slight change. Now, we didn't talk about it too much explicitly, but when we were deriving the cable equation in Chapter 6, we pretty much assumed the extracellular space was all grounded. And what we're going to do now is we're going to take electrodes and stick them in the extracellular space. So we can't ignore what's happening in the extracellular space. So we want to rederive the cable equation with not assuming the extracellular space is grounded. And I'm not going to go through all the steps, but you end up getting a term like this that was very similar to what we had before. This basically came from the continuity of current. The amount of current coming down from the left is different than the amount right. It's got to be going through the membrane. But notice that this is the intracellular potential here. And that's what really matters, is the voltage gradients along the axon. And that's going to be equal to the membrane current, which has 2 terms. One is C, and now I write this as the membrane potential across the axon, plus GVM. So we're going to, again, use not going to include the Hodgkin-Huxley opening and closing of channels. But this is essentially the cable equation we derived before. The main difference is that here we notice that this is the intracellular potential, and these are the membrane potential. And if you assume the extracellular space is grounded, those are the same, and it's exactly the equation we had. But what happens if we don't assume the extracellular space is grounded? Well, in that case, we can say that Vm is Vi minus Ve. And what I like to do is I like to get rid of Vi from this equation. So I'll just show that Vi is Vm plus Ve. That's just this equation solved for Vi. And I'll stick this up into here. So the only thing we're going to do is we're now going to get two terms, one with a VM and one with a VI. So you end up getting sigma I A over 2, and you're going to get a VE term. That's that term. And then you're going to get a VM term, which I'm going to move to the other side. So sigma I A over 2 V squared VM dx squared. So this term goes down to these two terms using this, plus C d VM dt plus G VM. Now I'll do what we did in class before. We defined a length constant, which was, first we're going to divide through by G. Then we'll define this as the length constant squared. So sigma I A over 2G square roots the length constant. And when we divide through by G, we get C over G, and that's going to be our time constant. It's really, G, remember, is a conductance, so it's the reciprocal of the resistance. So this is really an RC time constant. And the equation then becomes lambda squared d squared VE dx squared equals minus lambda squared dm dx squared plus tau dvm dt plus vm. Now, what this, if you grounded the extracellular space, this term went away. This would be exactly our previous cable equation. So you can think of this as a source term driving the cable equation. You're going to apply extracellular currents with an electrode. You're going to create some extracellular potential, and that's going to then drive your cable equation and stimulate the nerve. So it's exactly what we need to understand electrical stimulation. And in fact, this thing over here, this source term, is sometimes given a name called the activating function. And it will be what we're going to be looking at a lot. Because if you want to know where stimulation occurs, you look where the activating function is big. If you want to know what sort of, how stimulation occurs. So this is really what problem 7.38 was asking, is to drive a cable equation without the assumption of extracellular grounded and get the activating function. So it is very similar to what we did in chapter 6, a slight extension. Okay, questions on that? All right, well, let us now go to the next problem, which is 7.39. 7.39 says, for this problem, use the activating function derived in problem 38. Okay. Assume lambda and tau are negligibly small. Well, if lambda and tau are pretty small, this term and this term are going to be small compared to this. So that's really what I want to assume. Let's assume it's either near steady state or it's doesn't change rapidly. So these two terms are small. You just get Vm is equal to this activating function. So the activating function under these assumptions can give you an idea how much voltage is induced across the membrane. Then what are you going to do? We're going to consider a point electrode in an extracellular space, and we're going to calculate the transmembrane potential induced. So this is going to be our picture here. We're going to have, here's our axon. And we're going to have out here a point electrode. It's going to be injecting current, I, and the return current, you always have two electrodes. The other electrode's off at infinity, a long ways away. So we basically put one electrode in near the nerve. We have another ground somewhere a long ways away. And this is the x direction. And we're going to call this distance d. And we're going to put it in at x equals to 0. So if we're interested in, say, a spot right along here, it would be a distance x, and this would be a distance d, and this would be the distance r. Did I use big R? Yeah, between the two. And we know, and it's given in the problem, but we know that if you have a point source of current, you get a extracellular potential caused by the electrode, which is going to be 1 over 4 pi sigma E I over R. This should look a little bit familiar. If you remember from your basic physics, point charge Q produces an electric field or a voltage 1 over 4 pi epsilon naught times Q over R. Well, it's the same thing, except we're not dealing with a charge out in a vacuum. We're dealing with currents injected into a conductor. So what's important is the conductivity of extracellular space. So this is the conductivity out here. And what's important is how much current you inject. So here you have a voltage induced in the extracellular space, and you want to try to now figure out where is this nerve activated. All right, so let us do that. What we need to do is we need to calculate the activating function. So I'm going to erase some of this now. I'm not going to erase the big equation in the box. And what we want is calculate the activating function. First of all, we need to know VE as a function of x. Well, that's 1 over 4 pi sigma E over I. And then 1 over R. And we said R is this hypotenuse. So that's going to be d squared plus x squared square root. That's just Pythagorean's theorem. It is for this triangle here, which is a right triangle. So we now have V as a function of x. So let's go ahead and try to calculate it. First of all, we need the second derivative. So let's first calculate the first derivative. Okay. First, there's a bunch of constants. I over 4 pi sigma E. What is the derivative of this thing? If I want to, I can write this as I over 4 pi sigma E d squared plus x squared to the minus 1/2. That might make it a little bit easier to take a derivative. So what's the derivative of that with respect to x? Go ahead and say it out loud.
Take the negative 1/2 down.
Do the minus 1/2.
Then you would multiply it by d squared plus x squared to the negative 3/2.
Okay, so it's the minus 3/2.
And then multiply it by the derivative of the inside, which would be 2x.
2x, okay. So, we can actually cancel that 2 and that 2, and we get this expression. So, we have the first derivative. Second derivative is not quite so easy, because now we got to differentiate this thing. Okay, so I picked up a minus sign. I still have these constants. But now I have to differentiate x times this thing. So I've got a product rule to deal with. So how do I use the product rule? Basically, I have to differentiate x d squared plus x squared to the minus 3/2. That's the function once you get rid of all these constants with respect to x. So what's the product rule going to tell us? Who wants to help me out here?
The first term has a derivative of the second.
Okay, so the first term is x. And what's the derivative of the second?
Negative 3 times, well, negative 3x.
Okay, you're doing it.
Well,
Canceling already.
Okay.
Okay, keep going.
So times the function times d squared plus x squared to the negative 5/2 times 2x.
2x. I think what you had done is cancel those
Yeah.
2's already. Okay, and then that's this times this. How about the other one? So you got another term, which is derivative of this times that. Well, derivative of x I can do, so I don't need to rely on you guys. That's just 1. So this just gives you d squared plus x squared to the minus 3/2. Okay, so we're making good progress here. Now what I want to do next is I want to, let's see, I'm going to factor out. And some of this now is just kind of knowing the best strategy. This is really d squared plus x squared to the 1 over the 5/2. So d squared, factor that thing out. And let's see what's left inside now. Well, like you said, these 2's cancel. So I get a minus 3, and there's an x and there's an x. So minus 3x squared, and this thing's all factored out. Well, I factored out a d squared plus x squared to the 5/2 downstairs. This was only to the 3/2. So I really got to factor out the minus 5/2. That leaves me a d squared plus x squared to the 2/2, or 1, upstairs. So I really get a plus d squared plus x squared. So hopefully you'll follow that. And now this becomes minus I over 4 pi sigma e 1 over d squared plus x squared to the 5/2. And then upstairs is going to be d squared, and there's an x squared, and there's a minus 3x squared, so that's minus 2x squared. And that is the activating function. So really the transmemory potential, if we assume these two are both small, the transmemory potential is this times lambda squared. So we have our activating function right here, at least except for the lambda squared. If we wanted to make it the activating function, we multiply by lambda squared. And that tells us how this stimulates as a function of x. So that was just a little exercise in the math of taking derivatives. But now what we want to do, remember our usual procedure, is first we start with some physics. We develop a mathematical expressions, do some math to derive some stuff, and now we want to relate it back to the physics again. So how are we going to relate it back to the physics? Okay, so I'm going to have to erase some stuff. But before I do, were there any questions so far? Okay, I'm going to erase everything except this activating function. Okay. All right, we have two cases. First, we're going to talk about cathodal stimulation. So I is less than 0 is the cathode. So the way to think about that is if you have positive ions and they're going towards the electrodes, the current's going into the electrodes, you have a cathode. So that means if I is less than 0, then the voltage here is going to be less than 0. And if we wanted to see what that looks like, this would be VE. If we're just looking at VE now, it's 1 over square root of d squared plus x squared. So what's that function look like? What is a function of x? If I was going to plot VE as a function of x, what does that function look like? It's negative, so it's going to be on the negative side of the axis. What happens at very large x?
0.
It's going to go to 0. As this grows and it's in the denominator, it's going to go to 0. X equals to 0, it's going to just go to a constant. But it's negative because our I is negative. So VE looks like this. Okay, that makes sense. The voltage is biggest right underneath the electrode that falls off with distance. Now, if you wanted to plot the activating function, we can do it two ways. First of all, we can just do it visually. Activating function, it's the second derivative. The second derivative is the curvature. In this case, it looks like a parabola pointing down. So that's going to be negative. So you can have a negative value over here. Eventually it's going to go to 0 because it's flat. Here it looks like a parabola pointing up. So it's going to turn around somewhere and go up. And then it's going to be symmetrical. So you get something like that. Let's see if that makes sense from the equation. Well, at really large values of x, This is going to be x squared to the 5/2, so that's x to the 5th. And at large values of x, you have a minus x squared up here. So it falls off as x cubed with a minus sign. So this thing's falling off fairly quickly to 0 out here as 1 over x cubed. When x is 0, you just get d over d to the d squared over d to the 5th. You're going to get I over 4 pi epsilon sigma, so conductivity times 1 over d cubed. So the constant up here at the top is going to be I over 4 pi sigma e, and when x is 0, you get d cubed. D squared to the 5/2 is d to the 5th. D squared over d to the 5th is 1 over d cubed. And you can even tell where it goes through 0. When 2x squared is equal to d squared, it's when it passes through 0. So you can actually calculate what value of x it goes through 0. So the interesting thing is, remember, this looks like the transmemory potential. So when you stimulate, you get an area here that's positive transmemory potential, which means it's depolarized. Depolarization, you're raising the voltage from rest upwards, and that's going to cause action potentials to be excited. But out here, you get an area that's gone negative, you get hyperpolarization. So you get this strange little regions of depolarization and hyperpolarization. The depolarization is bigger, but the hyperpolarization is there. Okay, and if we wanted to, we could calculate, let's just worry about absolute values, so we don't have to worry about any signs. We could calculate the current. I'll call it IC for the cathodal current. Well, that's just going to be setting this thing equal to a threshold value, because this is really, if you multiply this by lambda squared, you get Vm. And if you say Vm has to raise to some threshold, say 10 millivolts before it activates the sodium gates, you're going to find that if I solve this, you're going to find you get V threshold. And here's the 4 pi sigma e d cubed. And I've been losing a lambda squared because the activating function is actually lambda squared times this. So there's the lambda squared. That is if I solve just for I. That's going to give you the threshold for cathodal stimulation. Okay. What we really want to do in this problem is we want to look at the ratio of anodal to cathodal stimulation. So let's look in the case of anodal, means the current is greater than 0. If the current's greater than 0, that means current is coming out of the electrode. So the voltage is just going to have the sign flipped. Looks like this. And the activating function is just going to have the sign flipped. So it looks like this. Now this is kind of strange because now you're hyperpolarizing. Remember, this looks like the transmemory potential. Right underneath the electrode, you're hyperpolarizing. It's an anodal stimulus. Remember, anode break, hyperpolarize the membrane. You hyperpolarize under the electrode, but you depolarize off to the side. So we have another way of doing anodal excitation, besides what they said in the Hachi-Husta paper. That is, if you stimulate with an anode, you're going to get depolarization, which could be large enough to open the action potential sodium channels and cause excitation. So what we want to know is we want to know what the threshold is for that. Well, that's a little harder because really you want to know how big this peak is here. So how are we going to figure out how big that peak is? Because we don't really know where it occurs. We don't really know what value of x. If we knew the value of x, we could just plug it in to our activating function and we could figure it out, what the peak is. Just like we plugged x equals to 0 to find that peak. How are we going to find where that peak is? How do you find where a function is a maximum?
Take the derivative on the zeros.
We're going to take the derivative and set it equal to 0. So we got to do yet another derivative. Do the derivative of this thing. We're going to set the derivative to 0. Well, all these constants don't matter. They're constants, so we can divide them out. All we want to know is where the derivative is 0. So we have to take d dx of d squared minus 2x squared over d squared plus x squared to the 5 halves. Okay, so this is not going to be too hard, but let's go ahead and do it. It is, again, the product rule. You can think of this as d squared plus x squared to the minus 5 halves upstairs. So you get minus 5 halves d squared plus x squared to the minus 7 halves times the top. Product rule. That's a squared, by the way. It's not very clear. And then you have the derivative to this one times that one. So you get plus. The derivative of this is going to give you x squared is 2x. So minus 4x times d squared plus x squared just to the minus 5 halves. And all that has to equal 0. Now that looks really complicated. But it looks complicated because you got all these crazy factors in there. But this is all equal to 0, so let's just multiply through by d squared plus x squared to the plus 7 halves. That'll get rid of this thing and make life much easier. So, I forgot one thing. Anybody see what I forgot?
The derivative inside.
Yeah, I forgot the chain rule. 5 halves, minus 5 halves, d squared plus x squared to the minus 7 halves, times the derivative of the inside from the chain rule. There's a 2x times that one. And then this one, I had the chain rule in because that was just this, which is to the first power, so you just got minus 4x. Okay. So what we can do is we can divide out a d squared plus x squared to the multiply through by to the plus 7 halves. And we might as well divide out this x because it appears in both cases while we're doing it. So let's multiply everything through by this. That'll make things nicer. This is 2's cancel. That x goes away from that x. The minus 7 halves will go away when we multiply by plus 7 halves. So all we have left is a minus 5 and a d squared minus 2x squared plus, okay, this x will go away when we divide by that x. We have a minus 4, so you get minus 4, and then this is d squared plus x squared to the minus 5 halves, and we're going to multiply d squared plus x squared to the plus 7 halves. So what it comes out to is 7 minus 5 is 2, so 2 over 2, it's 1. All we get is a d squared plus x squared, and all that's 0. So we're almost done here now. It looks a lot simpler. And in fact it is. You get a minus 5d squared here and a minus 4d squared there to give you a minus 9d squared. You get a minus and a minus are a plus 10x squared and a minus 4x squared gives you a plus 6x squared equal to 0. And now what we're trying to do is we're trying to solve it for x. Yes?
We still need to calculate the denominator.
We basically multiplied out the denominator.
Oh,
we're going to
okay.
eventually go back and plug it in to find the activating function. What we're trying to find is the value of x, where that's a maximum. So this trick allowed us to get rid of these denominators. Because this was to the plus 7 halves, that's to the minus 7 halves. So they just cancel. So it's a nice little trick to get rid of the denominators. And we can solve this, and you end up getting x is equal to the 3 halves square root d. So we now know where this function peaks. So if we want to know how big this is, it's going to be what? It's going to be I anodal. I'm only going to worry about the signs. I'm not going to worry about the minus signs here. It's going to be d squared minus 2x squared. X squared is 3 halves. and there's a 2, so I just get 3 minus 3d squared. I'm plugging it into this thing. 4 pi sigma e, I'm going to get a d squared plus an x squared is 3 halves d squared. 3 halves d squared, all to the 5 halves. We're almost there. That is anodal. Here we get d squared minus 3d squared is going to give us a minus 2d squared over 4 pi sigma e. And this is going to give us, did I get all that right? Yeah. This is going to give us d squared can come out. If you factor out the d squared, it's a squared to the 5 halves, so that'd be a d cubed. No, it wouldn't. D squared to the 5 halves is d squared to the 5th. Times 1 plus 3 halves. It's 5 halves. So you get this weird thing, 5 halves raised to the 5 halves. And finally, that's all. That's what the size of this thing is. It has to be equal to the threshold voltage, because in order to trigger an action potential. So what you end up getting for the anodal current, I'm only going to worry about sign, so I'm going to throw away that minus sign. I'm going to be kind of careless. I'm going to end up getting, let's see, we're going to get IA is equal to, you're going to set that equal to lambda squared. Lambda squared times that equals V threshold. So you're going to get V threshold times 4 pi sigma E, and you're going to get d squared over d to the 5th is going to give you a d cubed. You got lambda squared, and then you're going to get, when you solve for I, you're going to find that this is going to be equal to a 2. Let me make sure I'm doing this right. I really want to have it solved for IA. So you're going to get, actually, this is going to come down and be the denominator when I solve for I. So I'm getting 1/2 over 5 halves to the 5 halves. All right. That was a lot of work. What did I say I really wanted to know? I wanted to know the ratio of what it takes to stimulate cathodally to anodally. Well, the cathodal has the V threshold 4 pi sigma E d cubed over lambda squared. That's exactly what the leading factor is for the anodal. So if I take the ratio, those are going to cancel out, and I'm going to get that. Let's take the cathodal over the anodal is just going to be 1 over this factor. So I'm going to get a 1 over 2 over 5 halves to the 5 halves, which you can calculate. And if you calculate that, this comes out to be about 0.202. So what it's saying is that's close to 1/5. So it's saying that you have to stimulate 5 times harder with the anode than with the cathode. The reason is because this peak is about 5 times this peak. If I'd drawn it more accurately, it would have been about 5 times this wide. So stimulating with the anode is harder because you have a smaller activating function induced. But you do have some depolarization off to the side here. So to draw this picture and to make it a little clearer what's happening, let us extend this picture. You have, here's your nerve, here's your anode. So current comes out of the anode, goes into the cell, and then it eventually comes out of the cell and goes back into the extracellular space. That's the way of thinking about it, if you just want to think intuitively about it. So, where current comes into the cell, hyperpolarizes. So you get a big hyperpolarization here because you're driving current into the cell. But where you're driving current out of the cell, depolarization, but it's weaker because this current's all kind of focused here under the anode. It's more diffuse as it spreads out. So that's one way you can stimulate nerve axons with an anode or a cathode. And it's easier with a cathode, so most applications are going to use a cathode. When you just want to stimulate a nerve, you just stick a cathode down there and you can figure out, it's very sensitive to how far away you are because it goes as d cubed, but you can calculate what sort of currents you need. Okay, questions on that? All right, let's look at one more thing with this idea. This is problem 7.40. So, now I'm going to, you have to remember qualitatively what we found. We don't have to worry too much quantitatively about what we found if we want to look at this. Let's go and look at 7.40. Okay. Now, we know that when we're stimulating with a cathode, you're going to get something that looks like this. Depolarization under the electrode, hyperpolarization off to the side. Let us assume that if your depolarization is large enough, you get an action potential. So depolarization has to be bigger than the threshold. So T is threshold now, which is about 20 millivolts. 10 or 20 millivolts to start activating these sodium channels and get an action potential. That's what it takes to stimulate. But something we didn't talk about is hyperpolarization can actually block an action potential. If you hold the action potential down at a hyperpolarized potential, it gets farther from excitation. You can eventually hold it so depolarized, hyperpolarized, that you can block the action potential propagation. So if you, in other words, if you had action potential propagating along a nerve axon and you were hyperpolarizing the axon here, you could, if you hyperpolarize it strong enough, block the action potential from being able to propagate. Basically, it has to rise up to threshold, and it's got so far to rise that your action potential can't trigger it. So, hyperpolarization has to be bigger than B, where this is the ability to block. And it takes quite a bit to block, so that's more like 50 millivolts. And these are all magnitudes, so let's not worry about signs. You just know that this is hyperpolarization is in the negative direction. So what I want to do now is I want to look at what happens if we stimulate with a point electrode at different current strengths. So we'll start with a low current, really low current, almost turning your current off. Okay? So that your depolarization is less than the threshold. And if the depolarization is less than the threshold, your hyperpolarization has got to be less than block. Because threshold is less than block, and the depolarization with the cathode is bigger than the hyperpolarization. So if you don't, that means you don't stimulate. That means if you, here's your action, your axon, here's your electrode, and nothing happens. So you just get nothing. Okay. So if you, big surprise, if you have your stimulus low enough, you don't get anything. Remember, nerves fire all or nothing. So either you get up to threshold to start action potential, or you get nothing. Let's turn up the current to a medium current. So your depolarization is now above threshold, but your hyperpolarization is still not strong enough to block. Because like I said, this is only 20 millivolts. You got to get this up to 50, and D is stronger than H. Now you're going to get an action potential. Here's your stimulating electrode. It's going to depolarize under there. You're going to get action potential that propagates out, and you get propagation. These arrows represent an action potential propagating out both to the left and the right. They go both directions. Now I'm going to crank the stimulus up some more. So a strong stimulus. What's going to happen? You're still going to be well above threshold for the depolarization, but now your hyperpolarization is going to get big enough to block. Because remember, you're hyperpolarizing out on these edges. These regions. H, D. So now what happens? Now here's your electrode. You start the action potential is propagating outward from the depolarization, but this hyperpolarization out here blocks it, so it can't go any further. And you end up, if you're just down here with an electrode looking whether an action potential comes by, it doesn't. You get nothing again. If you're looking at the muscle that this nerve is attached to, you don't get excitation. So you got a weird situation where you start with your stimulator really low and there's nothing happening. You turn it up and you get excitation, but you can turn it up high enough and you can no longer have excitation. So, and you can actually use this idea for neural stimulation. I'll show you how in a second. So, does this kind of make sense to you? Okay. Let us see now how you can use a trick. The problem with this case is that you're propagating in both directions. Now, sometimes you don't want to do that. And let me show you an example of when you don't want to do that. Suppose you have a spastic situation. That is, suppose here's your nerve, and here's a muscle. And spastic means you're firing action potential. So you're firing action potentials all the time down here. And they're going down here and they're activating this muscle. Bang, bang, bang. You can't stop it. Well, that would cause a spastic response for your muscle. This happens sometimes with urinary incontinence. Okay, the muscle is what's going to open up the urinary sphincter so you can pee, and you usually don't want it firing unless you want to. But if you have a spastic response, it's firing all the time and causing, and then you can't control your bladder. So what you want to do is you want to stop the action potentials. And one way would be hyperpolarized, but that would take a lot of really strong stimulus. Let's think of another way. If you could stimulate here with a cathode, you could fire action potentials back. And these would collide, and it would block them. The problem is, the cathode would also fire action potentials that way, and they still stimulate the muscle. So what you really want is some sort of stimulator that only stimulates in one direction. If you can stimulate one way, you can have these action potentials block these, you stop the problem, but you don't keep the problem going. So let's see if we can design a one-way stimulator. And this is now really getting towards applications. So I'm going to erase this, and I'm going to show you how to make a one-way stimulator. Here's your nerve axon. And we're going to just do this kind of qualitatively. It's a little bit much to do quantitative now. We're going to have our cathode right here. Our electrode. Remember, it's a big volume conductor, just like salt water out here. And then we're going to take a little piece of plastic, and we're going to wrap it around the nerve axon. A little bit different. Let me put it right here. It's like a cuff. And thread the nerve through it. So it's like taking a piece of a plastic straw and having the nerve slid through it. So you have a straw like this. But it's asymmetrical. So the electrode's over here, and this side's shorter than this side. And you might say, well, that'd be very hard because you have to take the nerve and thread it through the straw. But imagine taking a drinking straw and making a slice at one place so you can open it up, slip it around the nerve, and then let it kind of close up. And now you basically have this straw around the nerve. Okay, now, here's the current. This is going to be a cathode. So the current's going to be coming into the electrode, and it's going to come in like this, but this side has kind of the lower resistance to the bath because it doesn't have this long, narrow piece here. So you have a fairly strong current coming into this cathode, where this is going to be fairly weak. So if you looked at the activating function, and this is where I kind of wave my hands because we aren't actually proving it, it's going to look a lot like it did before, but it's going to look more like this and more like a small magnitude and spread out over a large distance because you don't get as much current over here and it's spread out. So now you depolarize under the electrode, you hyperpolarize here, but you get kind of a weak hyperpolarization there. Now you turn up your stimulator. Start off with nothing. Turn it up until you begin to fire action potentials, and they're going both directions. You turn it up even more so that this area hyperpolarizes and blocks. But this is still too weak to block. So there's a range of stimulus strengths where your action potentials start out this direction and then block, but they still go this direction and don't block. And you now have made a one-way stimulator. And now you put that right here, and you'll fire action potentials this way, collision block these action potentials, but it won't fire action potentials that way, and you just cured this person of urinary incontinence. So this is one way you can use these electrodes and these ideas to sort of improve people's lives. I mean, neuroelectrical stimulations, a lot of these tricks are used to try to give people new abilities. So, one-way stimulators, it's really all you need is the electrode and a drinking straw, or something equivalent to a drinking straw, and you got it. So I think that's one of the cool applications. Okay. I wanted to tell you a few of the examples of what this is used for. And some of these, you actually have videos, which I'm going to email you the link so you can see them on YouTube. But first of all, you can restore people who have had become paralyzed. If you're paralyzed because you had a injury in your spinal column, so that your muscles are still working, it's just the neural signals aren't getting from your brain down to your legs. So think of, what's his name, Superman. I don't think he's... Pardon? Yeah, Christopher Reeves would be an example. Okay, had an injury, so he's in a wheelchair. So now what you do is you go down and you can stimulate down the nerves that are coming out of the spinal cord down towards his leg. And if you stimulate them just right, you can let him to move the leg. And then you can stimulate the other side. And if you kind of do it just right, you can actually restore some motion, some ability to walk. It's usually not great walking, but I've seen pictures of people who have gotten onto bicycles and had their neural stimulation restore their ability to do this, and they can pedal along, and it really can improve their quality of life. You can restore some ability to do your hand. Maybe you can't play the piano, but if you can grasp something, all of a sudden you can feed yourself where you couldn't before. These kind of neural stimulation ideas are used. A lot of the original work happened at Case Western Reserve over in Cleveland. They have a big neuroprosthesis program, but now it's gone to all other places. People are doing electrical stimulation using a lot of the ideas we talked about, restoring people's ability to move. Another big example is cochlear implants. Some people are deaf, and it really depends on why you're deaf. But a lot of people, the way the ear works is the ear has inside the cochlea, is inside the ear, and there's two membranes that tend to respond to sound by moving relative to each other. And there's these little hair cells that then get sheared, and those hair cells are what trigger the nerves to fire. So if you're deaf because the hair cells are no longer functional, and your nerve is still functional, but they just never get fired because the hair cells are shot for some reason, what you can do is you can stimulate those nerves. And the cochlea looks like this. The cochlea is kind of this spiral thing. It looks like, let's see if I can draw it better. It kind of comes in and it spirals down like this a little bit. And the membrane is somewhere kind of in the middle here. But what you can do is you can slide an electrode in there. And you can put electrodes, or slide a wire with electrodes along the path. Now the interesting thing is in the cochlea, different points along the cochlea corresponds to different frequencies of sound. so that you're almost doing a Fourier analysis. If you can stimulate at a certain point, you will get a high pitch, and at certain points you get a low pitch. So you can pick out different frequencies. And then all you got to do is you got to be able to have a sensor, a microphone, detects the sound, and then a little computer that tells you, okay, if I hear that sound, I need to stimulate certain electrodes. It Fourier analyzes the sound signal, picks out the electrodes to stimulate, stimulates them, and all of a sudden you've restored hearing to a deaf person. Okay, so that's another example. A cochlear implant, these are called. And it's another way that you can use electrical stimulation to restore some sort of function. And these are sold now. I mean, this is a big business, cochlear implants. And there are videos. I'll show you one video. I'll send you of a person who I believe the video talks about how they work. I have seen videos, I don't know if it's the one I'm going to send you, of show little kids who've been deaf ever since they were born. So they never even experienced sound. And then they get one of these input, and then they're all, they're so excited when all of a sudden it'd be like you'd never even experienced this sense before, and now you're experiencing it. You have to be deaf because your auditory nerve still works, but the hair cells don't. If you're deaf because your auditory nerve has a problem, this won't help you. But a lot of people are deaf because of the hair cell problem. This is another example of physics applied to medicine and biology. And then another one. Another one is deep brain stimulation. And this one, we don't quite understand why it works as well as some of these others, because you're stimulating neurons in the brain which don't have this nice cylindrical straight axon shape like peripheral nerves do. So I can't give you all the details, but it's been found that a person who has Parkinson's disease, they're usually going to have some kind of tremors. And if you stick electrodes deep into the brain and you stimulate fairly constantly, the tremors go away. And like I said, we don't totally understand it, but it works. So one treatment for Parkinson's disease is to install these electrodes. So what you do is you go in for brain surgery. They install the electrodes. They hook the electrodes under the skin down to a little unit that's usually kept in the chest or somewhere, which has the battery and maybe some electronics to tell you how much to stimulate. And then you can recover all kinds of function. And the interesting thing about this is that when they're doing the surgery, they have to know where to put the electrodes. So they usually do the brain surgery on these patients while the person's awake. And the video, I think this video is the one I'm sending you. The video shows a violinist who, towards the end of his career, had Parkinson's, beginning of Parkinson's, and you can't play the violin with tremors. So what they did is they gave him the violin in the surgery. They had his brain opened up. They were sticking electrodes in. They put it in little ways. They say, try to play something on the violin. And you say, oh, you can't play. And then they get the electrode just in the right place, and he was sitting there playing these beautiful violin solo in the operating room. They had cured the Parkinson's. Basically, it may not work 100%, but it works quite well. It worked well enough for this guy to be able to extend his career ways. So another example of electrical stimulation with nerves. We will do a lot more about electrical stimulation when we get further along in this chapter and talk about the heart. And then we're going to talk about pacemakers and defibrillators, which is another example of electrical stimulation. But just the neural implants are amazing. And people are even trying to develop neuroprosthesis to restore vision. That's an even tougher thing to do. But they have had some luck at restoring some amount of vision. So it's amazing what you can do with these. All right. I'll show you one more thing. We've got a few minutes left. I want to show you physiological recruitment. Let's see. Okay. Suppose now, let's remember the activating function. We've only been looking at its distribution in space, but it had this factor of lambda squared out in front of it. That means fibers with a bigger length constant tend to get stimulated easier because of this lambda squared. Because remember, lambda depends on the radius. So, what that means is you can stimulate large fibers very easily. Stimulating small fibers is harder. Often that's exactly the opposite of what you want to do. Suppose you want to restore somebody's function. You don't want to restore this motion. You want to restore this motion. Okay, so they have a little bit of delicacy. They can move these small amounts without moving the great big, huge motions. So we need to stimulate the smaller fibers without the larger fibers. That's called physiological improvement. So let's see how you do that. Here's the small, here's the large. Okay, very weak stimulus. Both are below threshold. You get nothing from either case. Okay, that's like no stimulus. That doesn't tell us anything, but it's where we start. A weak stimulus. Weak stimulus is going to now be able to stimulate the large axons because they've got the bigger lambda squared. But you don't stimulate the small axons, so you just get the large. That's just what we said we didn't want. We didn't want the large gross motions. We wanted the fine motions only. So we keep turning up the stimulator. Eventually, you're going to stimulate with a medium stimulus, and you're going to be able to begin to get the small fibers too. Well, now you've got the small fibers, but you still got the big fibers. Let's crank it up even higher, strong. And now, remember this action potential block? The large fibers, the hyperpolarization may get large enough so that these fibers are blocked at the hyperpolarization area. So you get action potentials that propagate, but then they block, so you end up getting nothing going out. You still have the small fibers. And now you have what you wanted, just stimulating the small fibers. And if you turn it up super strong, you eventually get to the point where you get nothing, and then you're back to sort of useless. But there's this range where you can tune it and get just the fibers you want to get. So if for some reason you want just the large ones, you can do it. If you want just the small ones, you can do it too. There are problems with this, these real strong stimuli. If you tend to get distant axons firing that maybe you don't want, you can get electrode effects at the electrode surface that maybe you don't want. So it's not an ideal case, but it lets you do things that you couldn't do otherwise. So, what a real modern electrode is going to look like is here's your nerve, cross-section. Here's some myelinated big axons and some small axons unmyelinated. Okay, and there's thousands of them. I'm just drawing a few of them in here. What often you'll do is you'll take one of these like a piece of a drinking straw and you'll wrap it around here and you'll hook a bunch of electrodes. These are the electrodes to it. And you can stimulate, and now you can do all the stuff we talked about. Plus, if you stimulate this electrode, you just pick up these fibers. Stimulate this, you just pick up the ones nearer to it. Because remember, it depends strongly on this distance, this d cubed. So you can pick out, you can do all the things we talked about, plus selecting different regions. It's hard to get the ones right in the middle selectively, but you can at least pick out different regions of fibers. So nowadays they got all these fancy electrodes that they can implant and do all sorts of marvelous stimulation. Okay, that's what I have today. For those of you who may have come in late, I have the exams. You can come up and get it after class. We have homework, but it's not due until a week from Friday. So we will talk more about it next class. And starting next class, we'll start talking about nerves some more. We're going to slowly transition into talking about the heart. So by middle of next week, we're going to be talking strictly about the heart and all its electrical properties. Okay, I will see you on Monday. Have a good weekend.